classifying them. No, you can get allochthonous carbonates, ironically. Not many of them for obvious reasons. What's the other? No, you had one shot. Let's give somebody else a chance. What's the basis of classification of terrigenous rocks? We have pardon? The what? No, we talked about the classification of terrigenous rocks. What are the two things we use? Grain size and composition or mineralogy. Well, when you look at carbonates, calcium carbonate is calcium carbonate is calcium carbonate. That's not strictly true because we have aragonite, high magnesium calcite, low magnesium. There are mineralogical differences, but in general terms, when you're looking at limestones, you're looking at what we can describe as monomineralic rocks. They're made up dominantly of one mineral. So what is an important component of the classification of terrigenous sedimentary rocks, mineralogy and then grain size, is not available to us when we deal with carbonates. Because they're dominantly monomineralic, the texture of the rock becomes a much more important component in classifying carbonate sedimentary rocks. So textural considerations are very important when it comes to identifying and naming carbonates. So when we look at limestones, the calcite that we see present in a limestone is typically present in two distinct textural forms. We have what are known as allochems, which is a fancy word for a carbonate grain or carbonate particle, and we have orthochems, which are essentially dominantly spheric calcite and micrite, where micrite is a term used, the full term is microcrystalline calcite. Micrite is a shortened version of microcrystalline calcite, and by that we mean calcite crystals that are less than 4 microns in size. In other words, obviously very fine-grained calcium carbonate. Okay, so allochems. Allochems are particles of calcium carbonate that form in a variety of ways, and we'll look at the variety of ways in which they form in a minute. And after they are formed in the shallow, warm water and marine setting, they can be moved around by current activity and deposited as clasts. And that's why some biochemical sedimentary rocks have a clastic rather than a non-clastic texture. And there are two major groups of allochems that are recognized or identified. First are the skeletal allochems, and obviously the second category would be non-skeletal. And obviously when we look at skeletal allochems, we are looking at fossils essentially. The skeletons involved can be an entire skeleton, which is particularly true when you deal with microfossils such as forams and other planktonic types, or they can be skeletal fragments, which typically is the case where you have, say, a clam or a gastropod that is in its own right a sizable chunk of calcium carbonate, but through a variety of biological or physical activities, that skeleton gets broken into smaller and smaller pieces. So Pool skeletons typically are microfossils. They tend to have the entire skeleton preserved, which is very useful because it allows you to identify them quite accurately, whereas a fragment, depending on the size and the shape of the fragment, you might not even be able to tell which larger group it belongs to, let alone be able to identify it to species. The skeletal alatens, which I suppose if I think about it, is another term for fossils, of different fossils in different states, are extremely important items because, in addition to helping you in a sedimentological sense in terms of identifying and naming the carbonate rock that you're working with, you can use the information from these skeletons for biostratigraphic purposes, age dating, if you will, of the rock, and also for to extract paleoecologic information from the rock. Because ultimately, one of the interesting things about sedimentary rocks is one of the things that people want to do and like to do is to use these rocks to extract information from them that tell you about the conditions under which the sediment accumulated. We've already talked in terms of terrigenous rocks where grain size and energy can be related, high energy, low energy. Skeletal alatens are important to us because, unlike a sand grain, a silica sand grain, a quartz sand grain can tell you stuff about hydrodynamics, tell you about current activity because the grains could be moved to form cross-bedding, for example. But a quartz grain doesn't give a damn whether it's being washed around in fresh water, salt water, warm water, cold water. It doesn't care. It just responds to what's going on in the environment. Organisms are sensitive to the environment. They're sensitive to temperature. They're sensitive to salinity. And they're also sensitive, obviously, to current activity because they can be moved around just like the sand grain. But because they're sensitive to a wider range of environmental factors, it makes them of more interest to us and of more importance to us, particularly from the paleoecological consideration. In other words, being able to extract information about the environment at deposition. Okay, so as I pointed out, that microfossils are most likely to be preserved pool, where the larger invertebrates are typically present as fragments. And so here's an example. Not a calcium carbonate is in this picture. This kind of monotonous purplish color, whatever it is nichrite, essentially. So that's the orthochem present in this picture. This is a shell of, I'm not quite sure, it's probably a fluorine. These would be the living chambers of the organism. Obviously, the soft tissue is decayed. Water has gotten in there and precipitated this starry calcite, which is filling the chamber. So this is a biogenic alchem. Obviously, it's a fragment, well, actually it's not a fragment. This is the whole specimen. These guys right here typically represent fragments of shell material that have been broken up by mechanical means, for example, and obviously nondescript in terms of your ability to identify. This guy, obviously, if you know the taxonomy, you can extract information about those guys, yeah. Pardon? Oh, you're talking. I don't know that the preservation there is good enough to identify that below a certain level. I'm not a boron expert, so I don't know. Yeah. Oh, this actual rock? Yes, this would be a biomicrite. And we're getting ahead of ourselves when we talk about the classification schemes in a little bit, but yes, this would be an example of a biomicrite because you have biological alchems embedded in a fine-grained micritic matrix. And this is another plot, so again, nondescript sense, because it's undergone a process known as mitricization, in which the internal structure of the skeleton has been destroyed by algal activity. But again, you see the body cavity is filled with sparse calcite. The blue coloration here is a dye, is an epoxy actually, where if you're dealing either with loose sediment or poorly cemented rocks, they often embed them in an epoxy to make them hard, where you can cut them and polish them to make thin sections of them. So you can see on the outside of this you can see the cement that has been precipitated on the outside of this and you can see the cement contacting this particle with this particle. This would represent in the rock before it was prepared for thin section would be porosity. So the kind of thing oil company people like to see. They like to see lots of holes in the rock, because the holes are more important to them than the rock itself, because the holes are where the gas and oil reside, obviously. So if we look at non-spherical allochems, there are three major categories that we can look at: coated grains, peloids, and intraclasts. If we look at coated grains first, these are particles characterized by the presence of concentric layers of calcium carbonate that form around a nucleus, a central nucleus. And so these concentric layers form the outer parts of what are often spherical or subspherical particles in terms of their overall geometry. They form in shallow agitated water, those conditions that we talked about earlier, and they roll around. And as they roll around in water that is saturated with respect to calcium carbonate, coatings of calcium carbonate form on the particle as it rolls around, building it up into slightly larger sizes. There are three major types, and the types are related to size in to a large extent: ooids, piezoids, and oncoids. If we look at the ooids, these are spherical particles. They tend to have a very small nucleus surrounded by these concentric layers of calcium carbonate. They have a size of less than about 2 millimeters. They typically fall into the 0.2 to 0.5 millimeter size range, which is the size of fine sand in the poisonous Wentworth scale type of situation. And as I say, these form on the seafloor by being washed back and forth. Typically form in depths of less than 5 meters. That's in large part because of the agitation component of the environmental setting. And this is what they look like. If you ever there's a beach in Abu Dhabi that I walked on, the sand on the beach, there are ooids, and it was weird because when you walk on the sand groans as these things rub against each other. They make a very distinctive noise. So you can see some of them are very, very nicely spherical, others are not as, and this would suggest to me that the nucleus of this fragment was perhaps a shell particle that had a slightly different geometry or shape to it, and that translates into the somewhat irregular, non-rounded or non-spherical shape that we see there. And if you look at a thin section, this is an example where somebody's taken individual ooid sediment, if you will, and embedded them in the epoxy, the blue color stuff there, so they can make thin sections of it. But you see that when we talk about the concentric particles, obviously this is what we are looking at in terms of concentric geometry. Piezoids, the second of the coated grain category, they're very similar to ooids in that they have this kind of concentric layering, but they tend to be much larger than about 2 millimeters. They tend to be not as perfectly spherical. The concentric layers tend to be crenulated, irregular, and it's suggested that the crenulation might be related to the fact that there might be some algal interaction associated with the generation of these concentric layers. Wrinkly. Okay. And then finally, oncoids, which are the larger specimens. These are larger than 1 to 2 centimeters, and you can see examples up to the size of your fist and larger. Again, they tend to have a somewhat more irregular shape, and they are also crenulated layers. And these guys are identified as stromatolitic in origin, in which there is a clear relationship between algal activity and the generation of the larger body, the oncoid itself. And so what happens is you have this ball of material sitting on the seafloor, and it has algae living on it. And it kind of gets rolled around. Of course, the larger it is, the more energy you need to roll it around. And as that happens, the algal filaments, which have mucus, sticky substance, tend to attract particles and stick the particles together, and they give rise to these layered structures that are roughly spheroidal in shape. Stromatolites as a whole, there are mat-like structures where algae grow on the surface of the intertidal zone and trap sediment, and you have alternating layers of sediment and algae, giving rise to layered structures. When they're somewhat spherical and can roll around, that's when they fall into the category of being referred to as oncoids. Yeah.
What sort of environments do chrysalid oncoids do they also form in water?
Yeah, they're typically shallow water phenomena, because the concentric nature of them indicates that they're rolling around, accumulating these layers. Okay, so yeah. Yes, shallow, warm, clear, agitated water, fairly shallow depth.
High energy?
High energy, yeah.
All of them?
Yeah. Okay, I'll stop there.